We are live. Welcome everybody and anybody out there to our first mathematics curriculum combo. Yes, I'm joined here by, you can't see the names, but I'm joined here by Lucy, or Lucy and I are joined together by Vicky, by Viola, by Andrew, by Charlotte, and by Joe. Welcome everybody. And we're going to talk about what the hell, rather than the other thing, is counting.
I take full responsibility for that.
Yeah, that title, Lucy, was definitely definitely one of yours. So yeah, I mean, counting is just number reciting, isn't it?
Yeah. Shall we just go home?
We'll just go home. You can recite numbers. We'll go home. That's it.
Well, quite, yeah. I think when we were choosing a first topic, it was important to us to think about something that cuts across. And so the idea of counting is particularly interesting to me because it's so easy to say, well, that's just early years. That's just the thing that kids do first. That's a very sort of easy way into mathematical thinking. It's the first thing they do. They have to get past it, you know, a bit like in some sense parts of reading, there's this kind of threshold. Once they can count, right, we move on to the next stuff, and it's all over and done with by the time they're, you know, 4, 5, 6, however old, and then that's it. Now they can count, right? And as Pete says, this kind of reciting part of that, and it's interesting watching your friends grow up with small children who are so excited about count, and you don't want to burst their bubble. You know, they have a 3-year-old who can count to 20 and they're like, okay, look what my 3-year-old can do, and they just say the words and you think it would be mean of me to interrogate your 3-year-old about how they actually understand that, but I really want to. So I say this as a parent myself, right? So I feel like I have a bit of a flexibility there, but not much. So
what understanding is behind counting then, Lucy?
I'm glad you asked, Pete. They said the chemistry would be electric. They weren't wrong.
Who said that?
I don't know. No one said that, did they? No one said that. I think that the interesting part for me is I looked into detail a little while back for some stuff, and I wrote a bit on the Mattock about it, and one of the things I did to try and understand this was interview some children, and not really interview, I just did sort of got on the floor and played with some children, and I think there are 7 or 8 different things that is a part of a kind of full rounded understanding of counting, and that's only kind of at the beginning, like counting a small amount of objects. And I guess the really important, interesting idea is that it's not really about you learn how to count to 1, and then you learn how to count to 2, and then 3, and then 4, and then 5. And at each stage, it's just the next thing. You know, it's a bit like when we teach kids to add, and we say we just teach them to add 2-digit numbers, and then 3-digit numbers, and then 4-digit numbers. And each of those is just the next thing we tick off, and that's fine. And there's so much underneath the initial, what even is counting about, that actually whether it generalizes and how it generalizes is kind of interesting, and there's a couple of interesting thresholds. So I realize I haven't answered the question yet, Pete. What's under one of the most important things being that there's a one-to-one correspondence between the thing you're counting and the counting numbers, which is kind of important. And when you have small children, they skip numbers, or they count 2 things as 1 sometimes, and so that instability. Even though they can recite the poem, they might say 1, 2, 3, 4, but they're just going 1, 2, 3, 4, and there's not one-to-one correspondence between the things they're saying and the number of objects, and that's really, really common. So, you know, I don't know if you can say your child can count if they can recite those things, but they're not actually understanding that principle. I think probably you might, and that's fine, but certainly that's for one particular thing. I'm going to pause because I want to see what Heather has anything to say about it.
So are you kind of saying that counting numbers is distinct from counting things in terms of how they're understanding it?
I am saying that, but that's actually not what I'm talking about here. Here I'm talking about attaching the number word in whatever language you use to exactly one and only one object. And there's this kind of secondary part of that, which is having a stable and repeatable counting poem, counting recital, which goes with that. So a kid could be really good at that one-to-one correspondence, but for example, they start at 0, which does happen, or they say 1, 2, 5, 7, 22. I mean, they don't, and then you've got a problem still. So it's not just the one-to-one correspondence, it's also the stability of the words in the language they're using, and keeping those in the same order, really important. So yeah, that's a really common thing to watch them get jumbled up with first, and it's quite funny.
Atul says, Atul's on the YouTube, and he says it all comes down to numbers, digits, and numerals as well. Oh, where are we at with that, guys? Numbers, digits, and numerals.
Oh, where's Mr. McCourt when you need him?
Probably off, I don't know, one of his houses in Portugal or something like that.
Yeah.
It's where I'd be at this point if I had one.
That is really, I mean, the difference between numbers and digits, I'm still not completely clear on. We've had so many conversations about this of late. But I guess the words for numbers and numbers are so inseparable in the way that we treat them that it's kind of, you can hear me struggling to articulate what I mean when I say reciting the counting poem. But I kind of, I know what I mean by that. And there is a sense in which the English language is not very well suited for counting, which you probably know about as well. It's quite hard to learn to count in English because it's really badly designed. Does anyone have an experience of that?
Yeah, certainly with my little one. Again, bridging that 10, 11, 12 area.
Yeah.
That was a big one for us when she was younger.
That's helpful. You can say how many you got, 11 and it never gets old. It's hilarious.
Yeah, I love that, to be fair. I even do that with big kids.
Yeah.
Which, interesting actually, taking that into the secondary realm, the number of kids, and I don't know if I'm talking about counting or place value or potentially both, that don't see 1,100 and 1,100 as the same thing, and being able to count up in hundreds like that.
Yeah, but why would you have two word labels for the same thing? Because we're mathematicians, we're supposed to be efficient.
Yes.
Good question.
Oh.
I think we do have this kind of system of representation in maths where we do try to be as efficient as possible and not call exactly the same thing by more than one label. And so I think the kid that doesn't get that straight away is quite smart.
It's a fair point, actually.
I don't know. It's one of those, really smart yet stupid yet smart questions. I don't think there are any questions, I guess. I haven't partway down this list yet, Pete, of things that I think you need to understand in order to count, I realise. Really important.
No, that's fine.
The order of relevance principle. So the idea that when you're counting a collection of things, you can count them in any order, but not say the counted words in any order, which is quite subtle when you're small. And that's really interesting because some kids really understand that mathematically, and it's such a powerful idea that sometimes order matters in maths and sometimes it doesn't. And recognising when it does is like one of the key aspects of a really good mathematical thinker. Being able to reason with, I need to see the number words in order, but I don't have to get this collection of stuff in the same order as I counted it last time, or indeed in any particular order if they're, all basically the same kind of object. That's a really interesting one to watch the penny drop. And I think pretty young. I think most kids who are sort of 3 and 4 quite often are grappling with that, and that's quite a fun one to play around with. What if I move this here? Have we still got 4? What if I take this one away but put it back over here? Have we still got 4? And they'll be like, yes, I know that. And then we've got the Cardinal Principle, which to some extent maybe is one of the most important parts of knowing how to count. That basically, if you say the words, the last one that you said is how many are in that collection of stuff. And it is so obvious as an adult and so not obvious as a child. And I guess
I was thinking about this actually, Lucy, when you said when I was looking back over your stuff, and I was wondering about something like having 8 objects, and I'm way out there now because we're into early years and key stage 1 mathematics, but having 8 objects and asking a kid to count the objects, and then when they get to 4 or 5, stopping them and saying, show me the 5 you've counted, or something like that,
in order to help them understand that a bit more.
Well, just in order to see if they're recognizing the 5 as part of 8.
Oh, yeah.
Sort of thing, which is related to, I assume, related to that idea of the last number you counted is everything is representative of everything you have.
Right. Absolutely. And that's
it came to me.
That's an even more sophisticated one, particularly when you're talking 5s and 8s, because that's a kind of in number is embedded thing, disembedding bits of number from other numbers and what we might call partitioning. And yeah, that's quite interesting to do that. I think that's a really interesting approach. But yeah, I mean, you watch kids and say, okay, count those for me, and they'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, and you say how many, and they'll go, I don't know. And as an adult, it's quite funny, but actually it's really not. You know, that takes a while to get that link. And once they have that link, there's also this idea that they don't have to start again from scratch. That you can have a collection. I can say, oh, I've counted those, there's 9. Oh, we'll put 1 more in, and still need to count from 1, because, you know, it's 2 things. It's the 1 more is the next counting number, but it's also like when I said there are 9, I meant I counted all of them already from the beginning. And so there's so much to unpack there. And if those aren't really clear in their head early on, you can imagine so many other mathematical principles just fall over later on because that's not completely clear to them.
Yes, I think Helen Williams often talks about that, doesn't she? She often talks about counting on as opposed to counting all, which I think is the sort of strategy for addition. So we're finding a link to addition there, aren't we?
We are.
What about links into secondary, guys? Anybody seeing parallels with that in secondary, in terms of that counting and having to start from the beginning? I mean, it's not necessarily the sort of thing we would hopefully, fingers crossed, see from secondary or higher learners, but are there?
I think
you would hope not, but there might be places where you do, and that's what I'm interested in. So what do you think?
Or maybe because they've skipped over that whole idea of counting and just number names, so they haven't really understood that properly.
Yeah, and then you get the place value issues.
Yeah.
But actually, what we're talking about here is term to term and nth term, guys. It's really complicated.
Yeah, it was fascinating watching my 5-year-old get to grips with. So it was just adding 2 things, and then watching him go from counting all to over several weeks or whatever. Just actually, I'm going to start from the bigger number, and then I'm going to count on, and that whole process was fascinating. Just watching that, and yeah, it's quite nice having children you can actually watch do that and realise actually quite how difficult it is to get that leap. And yeah.
Axel's made a good point, actually.
Yeah. Sorry, Pete.
Oh, sorry, Vicky. Go on. You go on.
I'm definitely finding it easier to relate this conversation to my own children than the children I teach in school. I'm thinking about the fact that how proud I was of my eldest. I mean, they're 10 now, but my eldest, when we were putting their shoes on, and every time I put their shoes on when they were tiny, I'd say 1 and 2 as I was putting their shoes on. And eventually, after a little while, I would say 1 and they would say 2. And I thought, my 2-year-old can count. And now I'm thinking, my 2-year-old learnt the poem of the numbers. That's what happened. I just remember thinking at the time, absolute genius child. But I found it so hard to relate this to the secondary classroom, because it feels like early years, like Pete said, it does feel like early year stuff that we wouldn't necessarily have to think about. So this is fascinating.
Well, I mean, I can definitely tell you another example of where it isn't, and that's factorial structures. It's exactly the same nested structure. You know, when kids are learning to do combinatorial reasoning, they quite often get thinking about factorials and start from the beginning when they're calculating factorials, and you watch the penny drop when they say, hang on, I just need to multiply by the next one from the previous one. And, you know, think how many types of sequence behave that way, you know, triangular numbers, adding the next one. That idea of nested structures is really, really prevalent much later, and quite complex, actually.
Love it.
And that's where I think it sort of came to me, is I could see other areas of maths where, you know, counting links, but that sequencing and the functionality behind sequencing is, and particular arithmetic sequences for addition, but also, like you said, factorial sequences as well. I think that's the bit that rang truest for me in terms of my experience as a secondary teacher.
Yeah. And let's not forget logic and proving, because we've got inductive reasoning and deductive reasoning right there as well. And so if they begin to make that leap between, you know, the next number is a +1 and it's the next one in the sequence, and, you know, once you've really got underneath that idea of n+1, which is actually really hard to explain to somebody who doesn't think, you know, about mathematics that way, like what does n mean, what is n+1, or like in computer programming, what's I, and people just go, well, it's a really hard concept to explain. You just go, well, it's just counting. But it's counting up to something or looping round and back. And there's so many processes of thinking mathematically and computationally that have that structure, I think.
And of course, Atul, we've got another comment from Atul, raises the point that he works with tutees that are dyscalculic or show dyscalculic tendencies, where actually even those early, like you said, one-to-one correspondences and things like that aren't there. They know the word sequence, they don't have those relationships, and they've obviously found it very difficult to form those relationships. He's talking about dice pattern subitizing is the first way he gets them to learn about one-to-one correspondence.
We should define subitizing, shouldn't we? Which it's become quite a cool word in the last few years.
It has.
Yeah, and some people use an S and some people use a Z, and guess what? Doesn't matter.
Oh, that's the American. Surely that's the Americanized form, the Z.
Right, but here's the hot scoop. This was really introduced by Clements and Sarama, and I haven't even said that right because he calls it Clements. And they wrote about this the most extensively, and they're both from the US, and so sometimes I use a Z.
Are you going to define subitizing for people then?
Sure thing. I mean, they would define it as they're using another word which is equally difficult, to be fair, recognizing the numerosity of a small set of objects. And numerosity, you have to then define that. So we're going to get this recursive definition problem. But numerosity just being, you know, the number of, essentially. But so I guess what's interesting about subitizing is there's some disagreement as to how many things can you subitize? Because the idea being that there's a lot of disagreement among researchers about which kind of systems you're using mentally when you're subitizing, and some people say you have different systems for recognizing small quantities of numbers, so 3 or 4 dots compared to much larger ones, and that's it's like a magnitude thing on a number line. Some people say it's the same system just used differently. Some people, you know, saying we can't possibly tell. But the idea of subitizing being that if I saw, and most people would suggest 4 and below is a safe bet, things, I could easily just straight away tell you that without doing some kind of counting, whatever counting is. You can I guess some would suggest subitize larger collections by decomposing them into smaller ones. So there are some people that say I can subitize 6, and some people say no, you can't subitize 6, and so it gets very controversial and interesting. And where is Helen Williams when we need her to tell us her definitive solution? But that's partly why dice games are so cool, and dice versions of collections of number can be really strong visual representations for kids and really fun to play with as well. Yeah.
Where does that link to a tens frame, say? Because I was quite impressed with, again, thinking about, it's so much easier to think about my own children, but doing some work with a tens frame with my youngest, and she just knew there were 10 immediately, just because it was arranged in a tens frame format. Yeah. She said 10 and 2 more, so it's 12. She didn't have to count the 10. I mean, she's 6, so I guess she's beyond the point of needing to count the individual parts anyway. Right. At the time, I was thinking that she would obviously see the two-ness of the 2 straight away, but the amazingness of that she saw that 10, I just thought, has she subitized there, or is it the tens frame? That's
genius. That is the answer.
It's the shoes.
Very proud. She's a prodigy. I think it's like anything. We have this sort of visual recognition system where we can shortcut the pattern spotting part of that. And, you know, if you play a lot of dice games, use dominoes even, a lot of people kind of find them about bit outdated, but the domino patterns, even cards, you know, also have a very distinctive arrangement of symbols, then yeah, kids will just start to pick up on it and spot it. But then there's all kinds of other things, like you say, with the 10 frames, where there's a color coding to them, right, as well.
Yeah.
And so there's lots of cues, and you know, having lots of different cues, you know, all the collection of 2 5s or whatever it is absolutely no bad thing. I think it's great and really helpful to kids who can start saying, yes, I see that, but being able to be flexible about that and move between them as well, so they're not only just used to seeing 10 as two lines of 5 or whatever they see it as, being able to say, this is the same 10, but it's just composed slightly differently. Obviously that is the power, because then later on they can understand that generalizes to lots of other types of number and really think flexibly like them. Yeah. Pete, you look like you're going to say something.
No, I'm listening intently at this point.
So can I ask something, going back to the sort of teaching the counting, because a lot of this sort of discussion about what numbers are and so on is kind of fascinating from a kind of, if it's sort of further on university and foundation stuff.
Right.
But I wonder whether the teaching to count, if you taught the bijection first of lining things up, and just are there the same number of sweets as people? Are there the same number of cakes as plates? Whether for those that find the number sequence, what were you calling it? Number poem?
Yeah.
Counting poem.
That they skip numbers or skip words or don't count, that focusing first on the trying to say, are these in a correspondence? Probably in not quite that language, but
I'm going to find my controversial button and press it. I think you said the first controversial thing. I like it. You said
a question.
Bijection of sets is what you said. Sorry? Right? Did you say bijection of sets? Do you want to explain what that means? Because even I don't understand that properly. I mean, I think. Okay.
Are we okay with set, or should I?
That's the controversial part of this, but go ahead.
Basically, that was a collection of things, and then bijection is really just lining them up so that each one in one group corresponds to something in the other group, and there's an exact match. Yeah. So the example, like, if have you got enough presents for everyone coming to your party? You don't have to know how many people there are, how many presents there are, if you just give one present to every person and everyone has a present and there's no presents left over. It sometimes goes with the pigeonhole principle.
Not knowing.
One could introduce it by having two collections of objects and saying which one is more, which one. And I wonder also
on with that, and that is one of my list of things. Underlying counting is the Equinumerosity Principle, and the I find it interesting that you wouldn't even need to know the number. That's such a mathematician thing to say. I love it. But the lining up of here's the set of here's the collection of children, here's the collection of sweets. Everyone gets one each. And therefore, I don't know about not having to know the number. I guess at the beginning it has to be, and therefore, if we know the number of one, we know the number of the other. The reason I said that's controversial is basically that this whole kind of counting is part of set theory versus counting is part of functions, or whatever else you want to call it, is kind of controversial. And how early you talk about set theory principles, and even talking about a set as a collection of objects, very serious mathematicians get very cross about this, I can tell you. And so it's interesting to me why. I'm kind of with you.
I wouldn't. I'm using that language here because I'm not a primary school teacher. I've never been a primary school teacher, so I wouldn't know what the right language would be. I obviously wouldn't walk into a primary school and say, right, we're going to look at a bijection between the set of cakes and the set of students. You would put it in the right language and context. I certainly didn't mean, but in slight seriousness, then it's just in part where I'm thinking of is that when you go beyond finite sets and go to infinite sets, then that equinumerosity is exactly the property that we try to keep. And so it's interesting to see how ideas from primary school are actually foundational mathematics. And when you were talking about numbers and the counting on, it's like the number 8 in one model of mathematics, the number 8 is 7 with one more thing.
Right. Yeah,
And
and
it's all those ideas that are actually foundation, that actually are the first ways children encounter these things are actually also the ways that mathematicians think of them.
Yeah, spot on. That's almost exactly how I would have put it. Yeah, I definitely agree.
So this sounds like count bookends a pupil's mathematical journey, where it's really important at the start, it's really important at the end. I'm still struggling to find a lot of practical relevance as a secondary practitioner in the middle.
It is, counting is tentacular.
Oh, go on, define that.
Well, it has tentacles and everything.
Oh, okay, you literally meant tentacles.
Yeah,
I thought you were using a fancy maths word that I hadn't heard of there.
Try not to. Basically, the whole can I count this? Well, let's go for I'm a discrete mathematician at heart, right? Does something exist? Can I count them? How do I know I've got them all? How do I know I haven't got repetitions? Do they need to be in a particular order? How can I prove to someone else I've got them all? Is so much of mathematics, and different bits of those at different times, right? But you know, I'm a really big fan of combinatorial ideas running all the way through, and I think that's what links all of these things in quite a lot of beautiful symmetry, really. That, you know, the idea of a logical systematization in mathematics starts from, how can I know that I have all of something? And that is counting. And then I want to prove it to you, and that is systematically ordering my count somehow, or diagrammatically presenting it to you. And then I start to use logic to say, well, if that, then this. And suddenly I'm into some really deep and interesting maths. So, I mean, that maybe wasn't very convincing, but I'd like to hear from other people if they agree. Do they think it's a bookend thing, or do they think it's a squid?
Squid?
Well, I said tentacular. I mean, it's a jellyfish.
Squid, not
I don't know.
octopus.
It's got bits everywhere.
Well, I'm starting to feel convinced. I don't think I've ever particularly given counting too much thought as a secondary teacher, but I'm feeling super convinced at the minute.
Hear that, Pete?
So, I do. I wonder how much.
Oh, I'm not taking sides.
No, I wonder how much that actually influences secondary teachers in their pedagogy and practice, though, or even Key Stage 2, you know, upper primary teachers, in terms of, you know, we talked about the big, clear, obvious one is in secondary GCSE level is teaching about the counting principle for, you know, the product rule counting, and being able to count, you know, the number of different ways of arranging objects or things like that.
Yeah, just maybe
even
define that clearly, just to make sure everyone knows.
Yeah, so at GCSE it's listed in the spec as the product rule for counting, i.e., you know, if there are so many possible outcomes from event A, so many possible outcomes from event B, so many possible outcomes from event C, then I can find the total number of possible outcomes by multiplying those three numbers together. And at GCSE they call that the product rule for counting. But even in teaching that, I can't think, and perhaps because I'm just not thinking hard enough, but I can't think of an explicit point where I draw on pupils' counting knowledge and understanding of counting. And maybe that's because I don't know enough about what would be considered counting knowledge and understanding of counting.
Well, see, I think the missing link here is combinatorial counting, and I would think this because that's what I've been thinking about for a long time and writing about. But, you know, let's see if I convince you. So a lot of these ideas from counting are about number, and to some extent are about discrete number, but there's some stuff about density, I think, that comes in later, and moving on to ideas of infinity and all the stuff we were talking about. But I think where they start to make a leap is here. When they have got this one-to-one correspondence, they start to line things up and count them. Great, they're in front of me, I can see them. Maybe even occasionally start to draw things and say, I can count these on the paper. So we're moving, you know, from manipulatives to something that's more of representation. Maybe there's quite a lot there that isn't quite abstracted yet. You know, we can see things and count them. We can hold up the fingers and see that they're the same, but there's still this fiveness of five that, you know, hasn't quite embedded yet, and that's fine. what happens when we start to make combinations is really interesting, because when I say, okay, we've got a big, jumble of cubes over there, let's put 2 together and see what we have. Like, we have a red and a green. Great. Okay. So if we start to make lots of these, how are we going to count them? Now, the problem here is you don't have one-to-one anymore. What you have is you're making something called a combinatorial counting unit, which is really exciting because it's much more complicated. I'm taking 2 things and I'm putting them together. And that is the basis for additive reasoning, multiplicative reasoning, all kinds of stuff. I'm taking 2 things, I'm making something else out of them. And I have to count differently now, because, for example, if I had just red and green in that box, I can now make, in theory, 4 different types of those little cubes put together, maybe a different number depending on how you count them, because I might say, well, if I turn them up the other way, I've got a new one, or red, green, and green, red is the same, so I'm not going to count that, or I can't have repeats. And all of this stuff is such important mathematical thinking, because it's contextual embedded decision making about how do I decide what to count. And that comes directly from counting, but it's much more developmentally interesting. And so at some point, you put the cubes away and say, I'm just going to draw pictures now. And at some really exciting point, I just start with red and green, and I start drawing lines between them, and I'm in graph theory, and it's really focusing on symbolizing, because it's like a reason to symbolize. Why do I want to draw a picture of this? Oh, because it's a pain to keep making all these cubes and putting them away again. Oh, this is really exciting. Or get Teddy stressed, which is the classic one. So, I really see that connection, but I don't necessarily see it happening in classrooms, because I think we've taken combinatoric stuff off the curriculum. Thoughts?
I think you can also link to geometry, because only ending this in part because of everything you said is brilliant. I love it all, but as you say, there's not a lot of that still in the curriculum, and so that you could have that as extension or sort of extra. But what's in the curriculum, of course, is geometry and area and counting, and counting is sort of the start of measure. Yeah, and then we build on that to working out areas, and that same idea of, if I've got an area here and I put another area bit on the side. Sorry, I've got my videos left, right inverted, so I'm not holding my hand in the right place. I've got an area here and I put an area on the side there. I can't get this right. Then the total area is the sum of those 2 areas. Right. And so that sort of counting on then becomes building on.
Right. But we're talking about addition there, aren't we? We're not talking about counting.
How is that not?
Addition is just glorified counting.
Oh, look at that.
Is it?
I love it.
Think of something that's not counting. That I'm struggling. I'm sitting here. Well, think of something that's not involving some counting. Then I'm struggling with that.
Yeah. But then at that point, surely the term becomes meaningless, because either everything is counting or very few things are counting, and there's nothing in between.
I think some things aren't counting. I will give you that. Shall I tell you what I think isn't counting?
Yes.
That's measuring. Now, bear with me. That's just one thing. I can actually think of quite a few things, but I think measuring isn't counting. I think there is a distinction to be made at some point between working with quantities that are continuous and that aren't. And not because I think there's a good statistical reason and we should only draw these graphs with some kind of, really not because of any of that, but it's about approximation. It's about when an answer is good enough versus exactness. And so when we're dealing with counting, we're mostly saying there's an exactness about that. If there are 4 things and you say 5, you're wrong. And, I did say I don't think maths is about right and wrong, but sometimes it is occasionally. And so if you're talking to a child and say, hand me 5 objects and they hand you 4, that's not correct. But if you say half that cake and give me half, they're never going to give you exactly half at this point. And you would, I hope not throw it back in their face and say that's not correct if they did something reasonably approximating a half. I was literally watching something the other day where somebody used the phrase a bigger half, and it made me laugh a lot as a mathematician, because what? But that's we do this stuff all the time. And so the idea that when you're measuring, you are also, there's 2 things going on. You're doing a kind of quantity thing, but you're also going, when shall I stop? When's good enough? What's a good enough approximation? And a really deep understanding of I will never ever be exact. It doesn't exist to be exact when I'm measuring. That's why I think it's different.
See, that's interesting. Well, yes, but that's interesting to me because I mean, I very recently actually with year 9 been looking at inequality and looking at the very talking about the very nature of numbers when we're representing them as inequalities, and the fact that there are infinitely many within this space, and that we might treat this as numbers behaving as continuous measures behave, rather than behaving as discrete objects behave. So, I mean, I don't know, that thought is not anywhere near fully formed yet, but it's chiming with me that it links to something that I've been having conversations with year 9 about very recently. And
yeah, I think I understand what you're saying, and I find, you know, like I said, the distinction between discrete and continuous is not only really complex, it's also sometimes it's not appropriate, and sometimes it is. And as you say, you can discretize, that's an actual word, continuous quantities, realize not a word, discrete quantities, and as humans don't really even perceive continuous in any real manner anymore. We don't really understand what it means, so everything is discrete to us really at some level. It's just about scale. This stuff is really messy but kind of interesting, and I don't know how much is appropriate to communicate to people. Is it easier to just say this is discrete and this is continuous and that's it? I don't know.
Are numbers discrete or continuous?
Depends what you're defining number.
Yeah.
Go on then, Andrew. Elaborate.
Well, I mean, number is a bit of a vague form. I mean, if you say what number am I thinking of, it's like, am I thinking of an integer, a natural number, a counting number, a rational number, a real number?
Why would there be a difference? Why would there be a difference between them? If would some be discrete and some be continuous?
Yeah. So, well, how technical do you want me to get?
As technical as you like.
If
we're not following it, we'll just ignore you and then go, that's interesting, and move on.
Okay. So Lucy just brought up the idea of approximation. Right, and that being the kind of fundamental, and I love that is the fundamental difference between continuous and discrete, that when you have something continuous, you have this sense of, you can approximate it, you can get close to it, you have this idea of distance. Discrete, it's just, I mean, the word means separate. The natural numbers, the integers are separate, they're apart. There's clear water between them. The real numbers, you've got this sort of idea of being able to say that 2.8 is quite close to 2.9 and closer than it is to 3. I'm just hoping I've picked numbers that work there. Where it gets a bit fuzzy is, say, with the rational numbers, because actually you could say rational numbers are continuous because you have that notion of closeness and how closely you approximate, but at the same time you've also got gaps between every, you can't sort of smoothly interpolate from one fraction to another because you have to kind of jump over all the irrationals in between, but there's still a sense that you would think of them mathematically as with this notion of approximation and all the structure that you need in order to have that approximation make sense.
But counting's just for early years.
Well, I'm not convinced any of this is counting yet, Lucy.
You're not.
It's all very interesting. I'm not sure any of it is counting.
Right, hold on.
Well, so I mean, what I'm trying to argue is that the counting is an example of measuring, and that area and things are other examples, and that there's an analogy that you can usefully use to transfer understanding and intuition from one area to another area. So I take Lucy's point about the distinction between discrete and continuous is really, really important, and is actually a big sort of stumbling block, or at least something that needs acknowledging and needs sort of thinking about carefully. But also this link between the two is really very strong. I mean, if you do the difference method on sequences, then you're doing differentiation. If you look at the summation formula for an arithmetic sequence, you're doing integration, but you're doing it in the discrete world rather than the continuous world.
Yeah. You know, I think I would tend to agree with that, and I think that the use of area particularly is really interesting, because essentially what Pete was saying there is what I think I would call the fundamental counting principle. So n ways of doing something, n ways of doing something else, n times n ways of doing it in total. And that's an array, and it's a Cartesian product. So there's no way to escape that being geometrical for me. And it's also for me the perfect midpoint between geometrical ideas and some really important statistical ideas, because it's a representation of decision points or attributes, depending on how you look at it. And so thinking about, classifying a decision point as I have, like a tree diagram, I have two choices here, I have two choices here, I have two choices here, that the counting part of that is, when can I count the structures and not the things anymore? And this, I think, gives rise to factorial structures, fractal structures, but also exponential structures. When I don't need to say I'm going to count every single one, it's exactly the same as geometry. I don't need to count every square, I can find the area. I don't need to count every branch on this tree, I can't even draw the whole tree. Hang on, what I need here is 2 raised to the power of how many bits there are. Beautiful.
Yeah, so that we don't need to be doing counting then. That's great.
What I'm saying is we are doing a generalized, sophisticated, efficient form of counting. We're just not doing what we originally called counting. It's an elevated counting. It's an elegant counting.
It's this sort of abstraction that you're no longer counting physical things that you can line up in front of you.
Right.
And you're having to now put them in your head.
Yeah, I think so.
I think I'd normally call that a counting strategy in my classroom.
Okay.
If I was talking about those things, like the area one you talked about, what's a good strategy for counting all of these squares? But I don't know
it's more
how.
than a strategy, though, because it reveals the structure underneath. I don't think it's just a strategy, because it's not like I can pick one of those and teach the kids one strategy and that's fine. It's actually revealing of structure. And that's what we find when we do combinatorics. Kids use the formulae and they don't understand what they're doing because they don't understand how the strategy reveals the structure.
Oh yeah, no, I get where you're going with that. So yeah, we'll look at different ways of counting it, and then we'll look at the fact that this is a general strategy that will work in all cases because of the structure of the rectangle.
Yeah.
And that's absolutely fine, but I don't know how that links to kids' understanding of what it means to count. Still not clear on that.
All right. So I think we talked about the Cardinal Principle. So the last thing you said is the number of objects in that collection, right? So that definitely generalizes to some of these ideas, because it's like saying I have a shortcut here to not start from the beginning, because I understand that this is nested. And like I was saying, for me, that's clear in factorial structures, that I never need to go back. I can just say where I've got to is the totality of the whole. And there is some set theory there probably as well. But I have understood that, and I don't even have to do that process. Somebody else can do it. Somebody can count in front of me and I can say, oh, okay, as a mathematician, I understand the structure of what you're doing, and I can be fairly sure if I watched you count that you have that many objects there in front of you, even if I don't see the objects. I think that definitely generalizes to how we communicate mathematics.
What do you think, guys? Some of you have been very quiet, and that's probably because we thought a lot. What do you think? Are you seeing that in your classrooms? Oh, we've lost Andrew.
Okay. I think I'm seeing the lack of it in my classrooms, and I'm starting to think that actually if we were doing it better, then the students would be doing better. I'm thinking in terms of just literally the teaching combinations in probability. And if you're selecting from 2 groups, how can you find all the combinations that are there? And the students just really struggling with just organizing their thoughts and knowing where they've got to and where to carry on from. And if they're distracted and then they look back, they feel like they need to start again. And I think a lot of that, and then all of this chimes with that I just wish that I wish I understood it better so that I could help them better, because I think that it always feels like there's a key thing missing of I'm saying to them, well, do this systematically. Let's list them. Let's join them up, and we'll try all kinds of different things, or let's organise them in a two-way table, or all these different kinds of ways. And I still feel like they are following a process rather than really understanding the concept of what we're doing. And I think that links quite strongly then with what we're talking about here. And then I'm just wondering how to make that leap. But you did say we could ask questions for practical applications, so maybe this is my one.
So just reframe that slightly. How can we make the leap?
So from just thinking about combinatorial counting and then using that sort of the systematic logicians, like there are 4 starters and 3 main courses, what are all the different options that you can pick, and sort of organising their thoughts and making that link there, because I feel like it's the same thing. Oh, I've got an echo.
The good news is what you've said there already, it sounds to me like really good practice. So encouraging a range of representations and specifically connections between representations is the general advice there. So stuff like tree diagrams, two-way tables and all of that. But even more than that, allowing students to create their own representations starts to get at how, as you've said, you can follow a process, and combinations is absolutely classic. This follow a process, just not understand what you're doing, because almost certainly you'll get a question where the question context changes, and oh, suddenly we've got 5 menu choices, or suddenly, you know, this counts twice and we need to change it. What do we do now? That's panic time, because I haven't understood the structures, right? And so them to really try and draw out then about how do they know they've got them all? How do they know they haven't got any repeats? What are they counting? So with stuff, you know, like where you've got decision points. So I'm doing, you know, 3 starters, 3 main courses, 2 desserts. If they're not able to communicate that in a variety of different ways, you know, like representing on the page, but also just exploring the structures they're using, you kind of think, well, that's one of the easier types of these questions, right? And so allowing them to create their own types of representation and communicate to another person what that means. So another person should, to some extent, be able to critique my diagram, look at my diagram, say, or represent, I'm using this kind of quite loosely, the word diagram, any kind of picture, and say, oh, I see you've got all them. I see that you have them all. And if I can't do that, I'm asking, you know, why can't I see that? Where's the ambiguity? And so, you know, the work I've done on this suggests that there are really key fundamental questions in the con we're talking about. How do we know we have them? Even more importantly, what are we counting? And what's really interesting is the context of the problem really matters. And so some kids will say to you, oh, I'm not counting that stuff because I'm vegetarian and I couldn't choose that. That's a brilliant thing to say. You might not get the mark for it in the exam, which is frustrating, but please let's talk about that, because in the real world that's really important. What does that do now? How many choices do we have if we're not going to say that one because you're vegetarian? And starting to be flexible about manipulating the problem in those ways, I think, is probably the key. But you know, I'm not the expert on this.
What about the rest of you? Are you seeing this in your classrooms?
I've just been teaching this, actually, so I was just thinking about it, and I've taught it. I've got 2 year 10 classes, and we're doing this topic at the moment. One's a high ability and one's a low ability, and actually I've taught it very differently to them both. But one thing I haven't done, and it's just when you were talking about the red and green cubes, and what I haven't done is anything based around that, where you've got the red and green cubes and you're literally saying, are these 2 things the same? Why aren't they? When you were talking about rotating them. And actually, I think that's just something I've never thought of, actually having that very specific conversation. But I think if I had, certainly with my lower ability mathematicians who can't just visualize as easily, that might have got me out of a really big hole later on.
What was the hole, if I can ask?
Just that it's really interesting, because the way they're relating things is really interesting, but it was when they were, we moved on obviously to sample space diagrams and tree diagrams, and I share this class with a different teacher who taught this area, but what they hadn't seen was a sample space diagram next to a tree diagram so they could link it. And that kind of, they just didn't quite connect that they were the same thing, but you just could show them in different ways. And I think if they'd seen something like the really straightforward simple cubes in the beginning, they would have made that jump more easily. Just that awareness that you can see it.
I think it's also worth saying that we are quite confusing in the way that we use tables in statistics.
Yeah.
In combinatorics, you know, quite often we use a Carroll diagram, which is about attributes and grouping, and then we expect them to be able to do a kind of sort of Cartesian product idea, which is a completely different thing. And then we're doing this two-way tables thing, which is actually a very different idea as well. And we adults quite often see the structure underneath fundamentally the same, but it's actually very difficult to get your head around unless you've really thought about it. That simple table of headings down here and what goes in them, especially things like when you're classifying, you can have multiple things in each cell. When we're talking combinations, we're saying specifically one thing in each cell, please, and don't double count and all that. And then of course that leads into, you know, double brackets expanding and cool stuff like that. So that structure of the two-way table I think is really, really important, and really quite often we don't explore it enough.
Cool. We've got a couple more comments that have come through over the course of the thing. Atul, again, thank you, Atul, for your continued contributions here. Counting is linked to place value and lots of other things. Link Roman numerals to numberness, Egyptian ones, multi-base. See, I was interesting that, because I was making this point today about, and it does. I'm not sure how much it links to counting. It links perhaps tangentially to stuff we've talked about today, but talking about the symbol not being the number, and using the Roman numeral as an example of that. You know, what does this symbol mean? Well, if you were Roman, it might mean this thing or it might mean that thing, depending on the context of what was surrounding it and things like that. And you know,
I think that's a very important point.
Yeah, and we talked about, because we haven't done circle measure yet, so I put a symbol up, I put pi up, and they've not, I mean, some of them have seen pi because they're very bright top set mathematicians and they've gone away and sort of looked at things, but many of them don't know what pi is yet, and we were talking about the fact that that symbol doesn't communicate meaning for them at this point, but hopefully at some point it will. So I think those links are definitely there. I don't know how much that links to counting.
Well, tremendously, and in two specific ways. One being that it is really important, as you say, to tell them that the representation of the number they use in their language, or you know, whatever they use to represent it, is not the number itself. Neither is it the number system, which is very confusing, but actually quite helpful once you start to unpick it. And then the second amazing revelation: there are other number systems in the world, both in terms of the symbols we use to represent it and the not you know, 10 based on 10 place value system. And my God, is that a revelation? Both of those things are a revelation.
Which is interesting, actually, because it links nicely to the other comment that we've had through from George, who I thought was going to be in the audience with us, but clearly is watching the stream on my YouTube channel instead. And he said, he mentioned that there are a few cultures that don't have counting at all in their language. The Paraha, I believe I'm saying that right, the Paraha Amazon tribe, that just have words for few or many, and that's it. And they don't actually.
This idea they don't have or use maths at all is not true. But this is just my opinion. And that, yeah,
I'm just wishing George was here now so he could have that argument with you face to face.
I think that, you know, that opens up a whole new question, because counting to some extent is the most fundamental mathematical activity there is. And, you know, we have some evidence that tiny babies and, oh my gosh, animals can. Are they doing maths? I'm going to drop that bomb and see what everyone else has to say about it.
Honestly, that was the first thing I thought when I saw that they don't use maths at all. I was thinking, well, I'm sorry, but my dog can count. So my dog knows when to say 1, 2, or 3 treats. And actually, if I split one treat into 3 parts, she feels happier, even though it's the same one treat. So I was, yeah, honestly,
she can count but not measure, is what you're saying.
she can count, but she definitely can't measure. And
They can. I tried it, it was fine.
Yeah, all the dog training things that I've read have said exactly the same thing. The size of the treat doesn't matter, but how many they get matters because they know. So I think, yeah, even tiny baby dogs definitely must be able to count. There's got to be some maths happening in this tribe.
Well, I mean, and that's the thing. Are they able to count, or are they just able to reckon more or less? And is that counting?
I think my dog is traumatizing.
I think they can recognise more. If you put 2 piles of dog food down, they will always go for the biggest pile. And I don't think it depends how many different pieces there are in it. So I think you can try it with. I've done it with I've got spaniels who eat everything, but giving them a small pile of and a big or bigger pile of the same number of exactly the same treats, and they always go for the bigger one. But then using different treats, so bigger treats but fewer of them, smaller treats and more of them, to see what happens then. And yeah, it's just quite interesting what they do. But I think they go for the one that looks more.
Can they add? So by which I suggest 3 treats and 3 treats. Someone holds the dog. You take 1 treat and add it to the 3 pile. Pretty much at the same time you let them go. What do you think would happen?
I don't know, but I really feel like I want to do it.
Well, that's it. I know at least 3 people on that call have got dogs. So crack on and report back, guys.
This next week is going to be a nail biter.
I think it depends, how far away they are from the treats. If they're quite a way away, as they go towards it, they're going to look and think that pile's bigger. But I think if they're very close, they're just going to grab.
Yeah,
because they've waited. But I do think if they have enough distance so that their eyes and think that pile's bigger, particularly if you've got more than one dog and they have to go to one or the other, then I think they'll go to more, and they can recognise quite small differences in more. So if you've got a bowl of treats where you've got, say, I don't know, if you've got 2 and 3, it's pretty obvious that one is more. But I think they can recognise quite subtle differences between bigger quantities. I'm not saying between, say, 30 and 31, but you know what I mean? Their ability to differentiate between more and less is quite developed. But I don't think they would say, guess what, was 31 in here? I think they'd just say,
well, we definitely need, I think, to put a shout out on Twitter this week for people to test this in various ways. I'm
going to try it with mine now, just to see what happens.
I think I've
because
heard of it.
You can extrapolate from the baby experiments where they also do things on screens, can't you, to see if they are acting in some sense. I would be fascinated to see what happens.
But is that counting?
It's less than more.
Go on, Andrew.
So I think I've seen this test or described where you put equal quantities in 2 bowls or whatever, and then you hide them, and then you obviously take one from one to the other, and then see which one they go for.
Yeah.
So can they tell that one has become bigger?
Yeah.
Yeah, I think it would depend on how much time they had to look at it. I think if they were just quite close, so they were just going to go because they were just going to grab one.
But they're not able to see what's in each pot.
Oh, I see. The bowls. Oh, right. Okay. I don't know.
Right, we have moved quite far away from talking about humans who apparently don't use maths, though. Quite different. Adult humans as well. They must do, because they must have all sorts of uses for maths. Like you can't function without it, can you? So there must be plenty of ways that they're doing it just without an official number system.
Yeah. I don't know what it means to have a number system, I guess, because the language isn't the system, kind of just as we were saying. And so much of the mathematics we do in the Western world certainly is like performative. Like we're so, especially as teachers, we literally narrate our thoughts, write down our thoughts, because that's the way we're used to doing maths. But it definitely isn't the only way to do maths. There certainly, I think, is a case to be made, a kind of inner monologue of thinking that maths is very much a mathematical thing, and so you just can never know if someone does maths. suppose, is the short answer. It doesn't
Yeah, you don't need the words for it to do it. So yeah.
Pete's not looking.
He
hasn't had a good one yet.
I still don't know what all of what a lot of this. I can see some of it with the combinatorics and all the rest of it. I still don't know how much of this has got to do with counting, in terms of, you know, how much of that I would call on when I'm teaching kids in the classroom, either upper primary or secondary. I'm still not sure how I would use that to impact and improve my practice.
I hear you, and I think to some extent that has to be a personal decision, right? But as always, it's about having the powerful knowledge to make those decisions in the moment. Sometimes you don't change hardly anything at all. It's literally you say, oh, but look, and then you draw a quick sketch of this thing and this thing. And like we're saying, so much of what we were talking about today is about isometry. It's about the same structure, but in different contexts or in different diagrams. And so being able to show kids that once they have understood a particular counting structure, whether it's a very simple one-to-one one or more extensive combinatorial one, once they can recognize that structure, there's actually quite a small number of them in mathematics, and they are used all over the place. And so recognizing that structure is used here and there and everywhere can be very helpful with problem solving, because it's a kind of shortcut. And I suppose that's what we're talking about. It's like counting shortcuts rather than just straight up counting.
And that I'm on board with, 100%. I like small numbers of structures that are prevalent in many what we would call
it's almost
areas.
Like I've read your book.
Well, I should hope so. You reviewed it, to be fair.
I did review it. It's very good.
Brilliant. Okay. We have been going on for a little bit over an hour now, actually. So I suppose we should really begin to draw this to a close. I'm not sure how long the stream actually allows us to be on here at all, but it seems like it's happy so far. So anybody got any sort of thoughts, questions, comments that they are thinking about right now as a result of this, other than I'm going to go away and test my dog? I'm considering something that we haven't talked. Well, I'm thinking about two things that we haven't talked about that sort of come back to me, which are, we talked about links to sequencing and things like that, but I think there's something within multiplication that I think would be worth considering more, because I'm a very, very big fan of the unitizing model for multiplication, and multiplication is creating a counting unit in effect. And so in terms of the links between sort of what you were talking about with step counting and things like that and multiplication, I think that's probably worth more thought on my part and more sort of more explicit consideration in my head. I very much like the sort of unitization thing, but how that links to pupils' early experience of counting and how that links into their later experiences of counting as well, I think is something I would want to think about more. And I don't know how this fits in with anything that we've talked about up to this point. I'm remembering an activity that I first did with Anne Watson, and I don't know if anybody else here has done.
Look, I knew you would.
Behave yourself. You've interviewed her. But I remember.
She's made me soup.
That's all right. Yeah, and I'm remembering an activity. That she had us do, and others potentially on the call have done this as well, which was counting back from 101 in steps of 1 1/10. Has she had anybody else do that?
I think
no, but it was someone else that was also. It also involves counting, actually. Yeah, go on, you finish yours.
Yeah, so so obviously what you get, I mean, it was talking about variation and things like that, but what you get is sort of, you go from 101, you get obviously 99 9/10, 98 8/10, because you don't simplify the fraction, 97 7/10, 96 6/10, and then you get to that point, of course, where you have no tenth. So you're subtracting the whole 1 and 1/10, so you skip the number. And you always get hesitancy in the lead up to that point because people know it's coming, and they're like, "Oh, I've got to make sure I get this bit right," and then they sort of go. And I mean, obviously that links to the idea of counting. I don't know how much it links to what we've been talking about with counting, but it links to counting, and it's something that just interests and intrigues me, that whole thought process. So I don't know if anybody wants to finish off talking about that and how it does link to what we've been talking about today or not, then great.
It definitely does, and the reason it does is the thing we haven't really covered today is thresholds and compression points, which is what you're talking about. Obviously all counting is not the same. Counting, you know, from 152 to 153 feels different than counting from 1 to 2, and that's to some extent about our conception of the mental number line, we think, and how that isn't completely linear and it's compressed, and maybe at some points it's not even linear at all. And we're still not entirely sure about that, but the idea that some numbers are more familiar and some numbers feel more familiar, and throwing fractions in there is a really interesting way to think about that as well, I think. But yeah, so the sort of where there's a compression point is I think what you're talking about with unitizing as well, where I can package it up and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is a unit which I'm happy with and I understand how it operates. But now I'm moving on to 11. There's a threshold there for all sorts of reasons, many reasons, and different people, I guess, will have thresholds at different points with counting as well, which is interesting as well.
Which I do think has considerations for us in the secondary classroom in terms of working with numbers of that type and stuff like that. Yeah, I'm not going to say any more than that, but I think there are things for us to think about there with that. But I can't say any more until I think about it more myself.
Future topic then, I think.
Potentially, absolutely. Right, unless anybody wants to say anything else or ask anything else, I think we're about there in terms of our time. So final pause. Marvellous, in which case, thank you very much for joining us this evening.
I think we lost.
He's done.
I'll finish that sentence for you, Pete. Thanks for joining us this evening. And we have very much enjoyed that quite lively conversation. And I think the intention is for us to trial this once a week and see if there's an interest. Pete, are you back now?
I am back, and the stream.
Right.
Oh, 1 minute. I thought I'd ended the stream, but I hadn't ended the stream. So clearly my fault. Bye, everybody. Thank you very much, everybody, for joining. Yes, thank you very much to our guests for coming along and offering their thoughts or just listening in. And thank you for everybody watching. And we are definitely going to end the stream there now that I have a connection again. It lasted all the way through, and just at the very end, it decided to drop out again. Great. Thank you, everybody. Goodbye. Hopefully, we'll see you again next time.